So, you ever look at something huge like GPT-4 and just wonder, how did that thing actually learn? It feels like it's got to be magic, right? Well, today we're going to pull back that curtain. And the secret? It's way, way simpler than you probably think. We're going to break down that whole process, piece by piece. Okay, take a look at these 3 lines of code. Get this. This right here, this is the engine. This is what trains pretty much every single neural network on the planet. I'm talking from the gigantic models at OpenAI and Google all the way down to a little side project you might spin up on a weekend. This is the beating heart of modern AI.
So, what are these 3 lines really doing? What's actually happening under the hood? Because sure, you can just copy and paste them and yeah, your model will train. But our goal today is to uncover the simple 5-step recipe that these 3 lines are hiding. This is the recipe that makes pretty much all of modern AI possible. It's that fundamental.
All right, so before we get to the recipe, we need to talk about the ingredients. There are really just 2 fundamental things we need to understand. Think of them like the flour and water of AI. You get these 2 concepts down, I promise everything else is going to click right into place.
Okay, ingredient number 1, the torch.tensor. This is the basic noun of PyTorch. Now, you can think of it as just a multi-dimensional array, but it's got a superpower. Almost all the time, the data inside is a floating point number. And you might be asking, why is that so important? Well, it's because learning, it's all about making these tiny little continuous nudges to the model's settings, right? You can't nudge a whole number, like 3 just a little bit. But with a float, oh yeah, you can go from 3 to 3.001. That tiny, tiny nudge, that's the whole game.
And our second ingredient? It's basically the model's nervous system. It's a built-in system in PyTorch called Autograd. And the crazy part is, you turn on this whole powerful system with just one simple command. I like to call it the magic switch, requires grad true. As soon as you type that, you're telling PyTorch, hey, pay attention, this isn't just data anymore. This is a learnable parameter. I need you to start watching everything it does.
So how does that magic switch actually work? Well, the moment it's flipped on, PyTorch starts building what's called a computation graph in real time. Every single calculation gets recorded. And each result, it remembers the exact function that created it. So this graph becomes a perfect map, like a trail of digital breadcrumbs. And that's the key. It lets the model trace any mistake, any error, all the way back to the source, and figure out exactly who to blame for a wrong guess.
Okay, so we've got our ingredients, right? We have our data, the tensors, and we've got our nervous system, Autograd. Now, it's time for the recipe itself, gradient descent. And the best way to wrap your head around this is to imagine you're standing on a super foggy mountain, and your goal is just to get to the bottom, to the lowest point. Your altitude, that's the loss. It's how wrong your model is. And the gradients? Well, those are the little signals that tell you which way is the steepest path downhill from right where you're standing.
And that foggy mountain analogy? It perfectly explains the 5 simple steps of the recipe. So, step 1, the model makes a guess. It's totally random, a shot in the dark. Step 2, it calculates the error. It compares its guess to the actual truth and boils it down to a single error score. Step 3, find the blame. This is where loss.backward comes in. It travels back through that whole computation graph to figure out the gradient for every single parameter. Step 4, nudge the knobs. Each parameter gets updated just a tiny bit in the opposite direction of its gradient. Why opposite? Because that's the way downhill. And finally, step 5, reset. You zero everything out and get ready to do it all over again.
Okay, enough theory. Let's actually watch this recipe in action. We're going to build a tiny model right now from scratch. And his only job in the whole world is to learn a super simple line, y equals 2x plus 1. So we'll start it off with totally random guesses for its weight, which we'll call w, and its bias, b. And then we'll just watch it learn the right answers.
All right, so the model makes its very first guess. And yep, it's a complete disaster, just like we thought it would be. The loss score, our measure of how wrong it is through the roof. But, and this is so important, this is exactly what we want to see. It has to start somewhere, even if it's completely wrong. That huge error score, that's the fuel that's going to power the whole learning process.
Now just watch what happens when we apply that 5-step recipe over and over and over again. This table here shows the progress. Each round, by the way, is called an epoch. So you can see at epoch 0, the loss is super high and our weight and bias are just random nonsense. But look, after just 10 rounds, the loss is already plummeted. And by the time we hit epoch 90, the model has almost perfectly learned the real values of 2.0 for the weight and 1.0 for the bias. The loss just keeps dropping as the parameters inch closer and closer to the truth. It's honestly incredible to watch happen.
Okay, so building that from scratch was awesome for understanding how it all works, right? But let's be real, that was messy. Can you imagine trying to do that for a model with 1,000,000 parameters? Or 1,000,000,000? No way. It's totally unscalable. And that's why, in the real world, we graduate from working with raw clay to building with, well, high-quality, standardized Lego bricks.
And PyTorch gives us 3 key pro tools to do this. First, you've got torch.nn.Module. Think of this as the standard blueprint, the master plan for organizing all your model's layers. Then you have torch.nn.Linear. This is one of those pre-built Lego bricks we were talking about. It just handles that common XW plus B operation for us perfectly every time. And finally, there's torch.optimum. This is like an automated builder that takes care of the whole update process for all the parameters, no matter if there's 2 of them or 2 billion.
And just look at the difference this makes. On the left, you see our messy manual code. We had to update and reset every single parameter by hand. But on the right, that's the pro way. The guess is just a clean, simple Model X. In that entire update process we did by hand, it's now handled by just 2 commands, optimizer.step and optimizer.zeroGrad. It's so much cleaner and just way, way more powerful.
So, look where we are. We've come full circle, right back to where we started. That whole complex dance of guessing, finding the blame, and nudging all the knobs, it's all boiled down, it's all abstracted away into these 3 powerful lines. You've got optimizer.zeroGrad to reset for the next round, loss.backward to calculate all the blame, and optimizer.step to update everything, all at once. This right here, this is the universal 3-line mantra you will see in, I'm not kidding, 99% of professional AI code.
Okay, so this is all great for learning a simple little straight line, but how in the world does any of this relate to a massive, mind-bending large language model like Llama or GPT-4? Well, this is it. This is the final and I think the most important reveal of this whole thing. The truth is, inside every single one of those modern LLMs, buried deep inside every transformer block, you'll find these things called feed-forward networks. And what are they built from? You guessed it. They are built with the exact same nn.linear Lego bricks we just used in our toy model. The incredible, world-changing power comes from just stacking dozens and dozens of these simple blocks together in really, really clever ways.
This table really just says it all. The core layer for our tiny model, it was nn.linear. And for an 8 billion parameter LLM, it's also nn.linear. The total number of parameters we had, 2. For them, 8 billion. The difference in scale is just astronomical. It's hard to even comprehend. But here is the absolute kicker, the most important part. The learning process, that 5-step recipe we just walked through, it is the exact same thing. So, what's the big takeaway here? It's this. Deep learning isn't some kind of incomprehensible magic. Not at all. Once you actually peel back the layers, you see it for what it is, a brilliant and just unbelievably scalable engineering process. A model is just a container for layers. A layer is just a container for parameters. And learning? It's just that 5-step recipe to update them all. The magic is gone. It's been replaced by engineering.
And just like that, you now understand the fundamental engine that powers the largest, most sophisticated AI models in the world. We went from a single number inside a tensor to the 5-step recipe and all the way to the pro tools that scale it up to billions of parameters. So really, there's only one question left to ask. Now that you understand the engine, what are you going to build with it?